Hello class, this is Mr. Hart, and in this podcast I want to talk about fluid pressure and flow. So we talked a lot last time about atmospheric pressure, but now we want to generalize it to any type of fluid and how we determine its properties and its flow and things like that. So let's get right into it. Let's start by talking about how we calculate fluid pressure. So the key idea we want to understand is that the pressure for any fluid varies with its depth. Okay. So in this equation right here, we can say capital P we'll use for pressure just like we did before, and it's still equal to the force over the area, but more specifically when we're inside the fluid we can also calculate it like this. It's equal to the density of the fluid, which if it's water it's 1,000 kilograms per cubic meter, times G, which is gravitational acceleration, times the height or the depth of the fluid, how deep inside the fluid you are. So for example, if we wanted to calculate atmospheric pressure, we just would need the density of air, how strong gravity is, and the depth or how much air is above us. And if you do that, you end up with 1 atmosphere or 101.3 kilopascals. But this allows us to use a whole bunch of other fluids as well. So let's try an example problem. So let's say you're an ecologist and you're looking at some fish at the bottom of some lake and you're determining how much pressure they can withstand, and you need to know how much pressure is at the bottom of that 15-meter deep lake. Well, what you would do is you'd say, well, pressure is equal to rho GH. In this case, we know that rho is water, right? So that's 1,000 kilograms per cubic meter. G is always 9.8, and the depth in this case is 15 meters. So we say that the pressure is equal to 1,000 kilograms per meter cubed times 9.8 meters per second squared times by 15 meters. We pull out our calculator, we times that out, 1,000 times 9.8 times 15, and we get that the pressure down there is 147,000 pascals. Now keep in mind when we calculate that, that's just for the water. In reality, if we want the true pressure, we would add 1 atmosphere to that. But we're just not going to worry about that for right now. So just use the equation as it is. Just keep that in mind. But there we go. That's how much pressure is down there. So really simple to use, and it's an easy calculation. You can use it for a whole bunch of situations. Let's do one more. So this is what I call the dam problem. The Hoover Dam uses concrete to withstand a pressure of 2.2 megapascals. What is the height of the Hoover Dam? So you can figure out the height based on the pressure that it has to be able to withstand. So in this case, we use this same equation, pressure equals rho GH, but we can solve for the depth or the height, right? So we can divide by rho and G and get that the height is the pressure over rho G. In this case, the pressure, I'm not going to write it down for space, but in this case, the pressure is 2.2 million pascals. We'll divide that by rho, which is still water, so 1,000. Don't forget parentheses. Times G, which is 9.8. And when we calculate that all out, we get that the Hoover Dam is 224 meters tall approximately, which is accurate if you actually go there. It's ginormous. It's crazy. So anyways, a very powerful equation that we can use. Let me show you some more applications of this. So here's a video that I do of a little tower that I have that has 3 different knobs. So when I pull the different knobs, they go at different speeds out of the tower. And here's a picture if you kind of missed it in the video, so you can kind of compare how much farther the top one goes from the middle one. And you can see that they're going out with greater force because there's more pressure based on the height. So if we were to draw this, okay, we can see that the top one has the weakest jet stream because it's the least amount of pressure. The middle one has a stronger one, and the bottom one has an even stronger one because of the different heights. Okay, even in something that short, right? I mean, that thing's not even a meter tall, but we can still see the differences in pressure in that tower. Okay, let's do another problem. Okay, this is a common problem. So practical application is, you don't see these around Utah as much, but in places like Kansas and the flat areas of the Midwest, they have to build water towers to provide water pressure. Here we just put the reservoirs on the mountains and we get water pressure. But over there we have to build them up in the sky so we can get some water pressure to people's houses. Okay, so standard water pressure in American homes is about 340 kilopascals. If this is the case, how high do these water towers have to be? Okay, so what we do is we just say, okay, well, we know the same thing. Pressure equals rho GH. In this case, we're solving for H, so we'll rewrite it as H equals pressure over rho G. Okay, the pressure is 340 kilopascals. Okay, and the density of water is 1,000 kilograms per cubic meter times 9.8. When we calculate that out, don't forget the parentheses, we get that standard water towers are about 34 meters up in the air, 34.7 meters up in the air, which is about 100 feet or so, which is accurate. The water towers have to be about 100 feet in the air to sustain enough water pressure for the town. Okay, so very powerful equation that we can use for calculating depths and pressures and things like that. Okay, so that's fluid pressure. Let's talk a little bit about fluid flow. So there's two types of flows that are interesting to us when we're talking about fluids. The first one's what we call laminar flow or streamline flow. This is when the flow is very, very consistent. There's not a whole lot of interaction between the particles. Things with very low viscosities flow more like this. Okay, this is less common though. More often than not, you'll get what's called turbulent flow when there's objects in the way or there's a lot of viscosity or interaction between the particles. You'll get more of a turbulent type flow. Okay, there's bumping into each other. It makes it more random and stuff like that. And so more often than not, we're dealing with turbulent flows, not laminar flows as much. But even with that being said, we can still figure out interesting things about these flows. Okay. So another thing to think about is different types of fluids and properties of those fluids. So we can come up with what we call an ideal fluid, and that's when a fluid receives no resistance as it passes through its container. Okay. Again, this is ideal. Most fluids aren't this way. They interact. Okay. But that's kind of something we like to think about, and when we do the math, we'll treat it that way. And then there's also a fluid flow rate that we have interest in, which basically describes how much fluid is going through a container in a given amount of time. Okay, our fluid flow is an important property of how much stuff we can get in a given amount of time. Okay, so let's think about flow. Okay, now if you have a container that doesn't change, just a big tube, the fluid should flow pretty consistently. But what if the container changes? Instead of being a big tube the whole time, it shrinks down. Or you may have seen this when you put your thumb over like a garden hose, right? The water will go slowly, and then you put your thumb over the garden hose and it goes really quickly. Okay, how can we describe that? I mean, obviously the water sped up in the tube, or what are we looking for? What's consistent here? What can we determine about our system? Okay, and this is the key idea. The key idea is this: the fluid flow rate for any point in the container is constant. That doesn't mean that the water, whatever fluid it is, isn't moving faster. It just is getting the same amount through in the same amount of time. Okay, so when you put your thumb over your garden hose, the water shoots out a lot farther because it's going faster. But the same amount of water goes through the hose in the same amount of time. The fluid flow stays the same. Okay, so if you go from a large opening to a small opening or vice versa, you'll get different velocities, but the fluid amount, the amount of stuff that comes through, will be the same in a given amount of time. Okay, So we can represent this equation with this, okay? Fluid flow is equal to the amount of area that you're covering, cross-sectional area, times by the velocity that it goes through. So if fluid flow is conserved, then our initial or starting fluid flow has to equal our ending fluid flow. So if we start with a certain cross-sectional area and then it's going a certain velocity, that has to be the same as this cross-sectional area times that velocity. The amount of fluid is the same. Okay, so A is area, V is velocity. Okay, which explains our garden hose analogy again, right? You put your thumb over the end of the garden hose, you decrease the area, so the velocity has to go up to keep the fluid flow the same. Okay, let's try an example problem. So a garden hose has a cross-sectional area of 5.3 centimeters squared, and the water is coming out at 1.8 meters per second. If you put your thumb over the nozzle, the area decreases to 2.1 centimeters squared. What will be the velocity of the water when your thumb covers the hose? Well, let's determine a couple things. Okay, so first of all, starting off, our initial cross-sectional area is 5.3 square centimeters. Our initial velocity is 1.8 meters per second, and our second area is 2.1 square centimeters. And we're looking for velocity 2, right? That's our question. So we just set up A1 V1 equals A2 V2. We're solving for V2, so we'll rewrite it as V2 equals A1 V1 over A2, right? Just by dividing by A2. We'll plug in those numbers on the left side. 5.3 times 1.8 divided by 2.1. And we get that the new velocity of the water coming out of the system is 4.5 meters per second. Okay? So that's how quickly the water has to come out to keep the fluid flow the same. Now again, we're assuming this is an ideal fluid. In reality, it'll be a little bit less than that because of the interaction with the container and your thumb. But overall, it's a pretty good approximation. Okay? Let's do one more just to make sure we got this down. So a river with a width of 5 meters and a depth of 3 meters forces water into a small opening. The water moves through the river with a velocity of 0.5 meters per second. The water going through the opening is moving at 1.5 meters per second. How big is that opening? Okay, so first of all, we know our first area, it's not given to us directly, but it gives us the width and the depth, which is just a big box. So we'll assume that it's a box and say that's 5 times 3 or 15 square meters. Okay. Then if we say, well, the first velocity is 0.5 meters per second, and the second velocity is 1.5 meters per second. Then we can solve our equation. A1 V1 equals A2 V2. We're solving for A2 this time, so we get A2 equals A1 V1 over V2. Okay, we plug that into our calculator. So we get 15 times 0.5 divided by 1.5, and we get that the area of the new opening is 5 square meters. Okay? And there we go. Now, I didn't mention this in the last problem, but keep in mind, if you keep your units consistent, you actually don't have to convert into meters for the area, as long as you keep your units the same. In the last problem, it was centimeters squared, and this problem is meters squared. It doesn't matter in these conservation setups because we'll divide that out. But just something to keep in mind. Be careful with it, though. Just make sure you always keep your units the same, and then they should cancel out. Alrighty, but that is it for this lesson. Okay, we covered fluid pressure and fluid flow. Go ahead and do the homework. Let me know if you have any questions, and thank you for watching.